So I was talking about the October event, and much closer to that, happening this Saturday, we will have an upcoming event in APU. APU is in Bukit Jalil. We often have once a month offline session, and this one is going to happen on the 17th of June, 11 a.m. in APU. These are the agenda, and feel free to just head on to the meetup page to just attend, and feel free to drop by this Saturday. I will be there, but many of the community will be there, so it's not that'll be nice for you to like say hello to everyone. And now finally, let me stop share, and I would like to introduce Cathie to talk about ZKML, and I will let her take the stage. So welcome, Cathie.
Yeah, thank you, Sichuan. Let me share my screen. So everyone should be seeing it all right now. Let me also grab the chat window. Right, so today I'm sharing about ZKML, zero knowledge machine learning. This is the first time that I have ever been speaking about ZKML for such a long time, like a long duration. So we are going to start from a little bit of basics, a little bit of crash course, and then we're gonna go deep very quickly. So bear with me in the first few slides. If anyone who actually already know about ZK, I apologize, but just so that we have everyone on the same page, I'm gonna start off like quite easy to begin with. Right, and I also prefer to take questions during the talk especially because it's so long. So if at any point anything is unclear to you, or you have any questions, just feel free to either like put it in the chat or something like that so that I can see it. Right, so this is today's rundown. Essentially what we're going to do is I'm going to break this into 3 parts, which is basically things that has already happened, or say a little bit of background or rationale, things that you're supposed to know already. And then we will talk about what is like the current like status quo, what are the challenges that we are facing in ZKML, what are some of the open source libraries that you must know if you're getting into ZKML. And then we're gonna hop into the future, which is, of course, I'm representing PSE to present this topic here today. So we'll talk a little bit about what kind of research we're doing here. Also, if you want to get started in ZKML, where should you get started? How can you get started? And at the end, I would like to kind of invite all of you to kind of let's just brainstorm and think about what we can do in this space all together. Right, so starting from the past, supposedly everyone who is into ZKML or who's interested in ZKML would know what is ZKP, which is zero knowledge proof. But just a really quick crash course in case you don't know what the heck is zero knowledge proof. So, well, zero knowledge proof, of course, means that we're trying to prove something to another person, right? And this is relevant to blockchain because a lot of the time we want a trustless or a trust minimized process, and it's very difficult to do that on the blockchain. So when we talk about zero knowledge proof on the blockchain, typically we're talking about the process that looks like this. So what you will have is that there's 2 entities that is at play here. So we have on the left-hand side who is the prover, and on the right-hand side who is the verifier. And this whole process is called a non-interactive ZK proof because there's no multiple kind of back and forth and interaction to it, right? So it's a one-off process, right? So the prover would be making some kind of a statement. That statement could be, so let me give a very easy example. Let's say I want to prove to you that I know how to add 2 numbers together, right? Or I know what numbers add up to 10. So there are a lot of choices, right? You can do 1, 9, 2, 8, 3, 7, 4, 6. You get the idea, right? And the idea is I want to show to you that I know how to add to 10 without letting you know what numbers I have in mind. And so here, I'm kind of also, as a prover, I'm going to construct a proof so that I can give you kind of a mathematical statement, a few numbers. And those numbers, according to mathematics, is going to tell you that I know how to add up to 10. Right? And you, as a verifier, on the right-hand side, I'm going to send you the proof, and you're going to run it through a verifier to check the proof. So for blockchain in particular, the verifier here is a smart contract. So it's not really a person or an entity. It's a smart contract that we deploy on chain so that we can have a trustless way of saying that, okay, I give a proof to this smart contract. This smart contract function is going to give me an answer, true or false, right? So if the proof is true, it will return true. If the proof is false, it will return false. So that's the kind of the basic idea of having ZKP. And really, there are three properties that you'll usually hear about ZKP, which it might seem very kind of self-explanatory and obvious, but I'm just going to put here regardless so that you have an idea of, what is a ZKP. So typically, when people talk about ZKP in the mathematical terms, there's three properties, which is completeness, soundness, and zero knowledge. So completeness just means that the verifier is gonna give out true whenever you are actually giving a valid proof, right? So the verifier is not gonna have false negative. I have a mistake in the slide here. I will change it up and afterwards. So I will provide the link to the slides after this talk as well. Sorry. So completeness is no false negative. So the statement here in the middle is wrong. Completeness means that there's no false negative. So if the prover is honest, then the verifier should always say that as a true statement. Whereas soundness is the converse. So soundness is saying that only if the statement is true, then the verifier is going to say that it's true, right? So it should be no false positive, right? So this ZKP process, the verifier is neither going to give false negatives or false positives. In other words, is 100% correct all the time. And most importantly, zero knowledge, right? So I can prove to you that I can add up to 10 by telling you the number 2 and 8, for example. But how do I hide those numbers and still prove to you this result? And that's where the zero knowledgeness comes in, right? So there's no information that is leaked to the verifier except for the fact that I want to prove that, except for the statement that I want to prove to you. So this is typically what we will see in a lot of classes, online materials. But really, there's one more important property, which is typically less talked about, but we make use of it all the time, and that is succinctness. And I want to emphasize this because it's an incredibly useful property for a lot of things that we already know, actually. Succinctness means that whatever we are trying to prove, the size of the proof itself is usually significantly smaller than the underlying computation, right? So it's saying that, for example, in order to actually do the computation, we might need 100 of code, right? Whereas the proof itself is, say, 3 lines of code. Okay, I'm just making these numbers up, 3 lines of code, right? But the beauty of this is that we know that blockchain is very limited in terms of size and computational resources. So this actually comes in handy. We'll talk about this again in a little bit. And in fact, we always use this property all the time. Right, so why do we want ZKML, right? Okay, so now we know what is ZK. Why do we want ZK or ZKML on blockchain? I would propose the counter question, which is, why not? Okay, just joking, but really, why not, right? Because Ethereum, after all, is called the world computer. It was originally proposed as, doing all the possible computation that a computer would do, right? And one of the problems we have right now is that there is actually a lot of limitation with the blockchain. And there's a lot of things that our computer can do that Ethereum can't do. For example, we know that there are mainly two limitations of Ethereum. So namely, first of all, the Ethereum has a limited block size and also contract size, right? So you can't really fit a lot of things into a block. You also really can't fit a lot of things onto a contract. A contract is around 24 kilobytes right now, right? So if you want to do very complicated stuff, you will probably have to break down your programs into a bunch of contracts. And that's not really what the blockchain is intended for originally. The other problem we have is, of course, Ethereum, like any other public blockchains, the transactions are fully transparent, right? So we don't get a lot of privacy here. Of course, it's pseudonymous, right? So we get, whatever we do is attached to an address, not our personal identity, but still everything is on the blockchain is kind of transparent for you to see. And with that, actually ZK can help tackle both of these problems, right? So for ZKML, there are two things that you can do, right? So just now, remember the fourth property of ZKP is succinctness, right? In other words, compression. So one of the ways that ZK could be helpful is to compress very complicated computations off-chain so that it becomes a very small proof, and that small proof can be submitted onto Ethereum mainnet for verification, right? And one of the examples that actually we all know about or all use nowadays is ZK zero-knowledge-based L2 rollups, right? And that makes use of this. In the L2, the block size is huge. How do we actually are able to verify these state or transition or state changes? And that's because we have this succinctness property of ZKP. And to tackle the second problem, where all the transactions are fully transparent, ZK can actually help prove ownerships of certain information like data or while maintaining privacy, right? So we all know about the famous tornado cache. That is one way that ZK can help maintain our privacy, right? There's also a lot of different ZK ID programs or projects out there that help maintain privacy. Right, but if you realize, so far I've put machine learning in the bracket because really we can have all of these already, right? Without zero knowledge machine learning, without ZKML. So why do we need ZKML, right? If we already can use ZK for a lot of different things, what is the need for us to absolutely put machine learning on chain? Right, exactly. So I will get to the next part. Yeah, I saw the question from Lucy. Yeah, so rollup has nothing to do with ZKML, but data has a lot of things to do with ZKML. Right, so with ZK already, we can prove that we possess certain data, right? So imagine if we're trying to prove some kind of data, currently without ZKML, what I can probably do is to say that, okay, I have a picture, right? Let's say a picture of me. I will be able to hide all the other pixels on this picture and just show you, like, essentially ZK is like covering my picture with a huge piece of cloth and showing just a little like peek, a little hole in the cloth to show you, hey, I have certain pixels in the middle of this picture here, right? So in other words, I have a picture where I can prove to you that I have certain pixel at, XY location that is of value Z. The problem with that is that it's not really a meaningful proof, right? Sometimes just with pure ZK, the proof we get is meaningful because maybe we're hashing something, maybe we're just trying to do mathematical statements, we're trying to prove numbers. But a lot of the time with other kind of data, this kind of proof is not very meaningful. And that's kind of why we need ZKML, because ZKML or machine learning itself will allow us to do a lot more than just data proving or value proving. It will allow us to do more like data indexing or data labeling, right? So imagine if we want to prove something about our data, right? Like something like, I don't just want to show you that there is a picture that I have certain pixel. I want to show you that I have a picture of a cat, right? This is something that just using CK alone is not going to help. We will need some kind of machine learning model, or, well, even if it's not a machine learning model, some kind of model or some kind of algorithm that is able to tell us that this picture is of, you know, a cat or of a dog. So this is something that the ZKML will come in very handy, which is to prove something about the data content itself. And that brings us to what is ZKML really, okay? So when we talk about ZKML, this is kind of the structure or the architecture that we talked about. And it kind of looks like this, okay? So the idea is that we have a zero knowledge circuit, okay? For those of you who doesn't know what is a circuit, you can imagine this is just a program that can perform what our neural network can perform, right? So NN stands for neural network. So let's say we have some kind of CK program that can already perform neural network operations. Then there are three types of data that comes in and out of this circuit or this program. So there are three types of data. There's input data, model weights, and output. And what these data represent actually depends on the use case, right? So let's give an example. So for example, if this is a stable diffusion model, right? Stable diffusion model that generates an image given a prompt. So the prompt could be something like an astronaut riding a horse, right? So that prompt itself would be the input data.
오늘 만난 그 멤버 중에 하나가
Wait, I need to
오늘
mute.
뭐 해야 되죠?
아니.
아산병원 부원장.
Mute. Sorry, wait, hang on. I think we're good now. Wait, hang on. Yeah, okay, I just muted everyone. Okay, sorry.
Oh, yep, no problem. So the input data would be the prompt itself, right? Which is an astronaut riding a horse. The output will be an image. And the model weights is just whatever the stable diffusion model has as its as its parameters, weight params inside the model. You know, another use case could be, let's say if our neural network actually perform a facial recognition, then the input data would be an image of our face. The model weight is still whatever the weights that the model takes in. And then the output is an encoding of our face, right? So essentially, our face is called Face ID on an iPhone because it encodes our face into kind of a hash or encoding a string that identifies our face. So let's say we can already perform that, and this is the kind of the whole construct of ZKML right now. Just want to make a note that we're just talking about inference or prediction, not really training yet. So model training is another thing that we're trying to tackle, but most of the time we're talking about inferences. All right, so this whole machine learning inference process, with this construct, we can have three types of use cases. And the first type of use case might be a little bit counterintuitive, but closely tied with what we were saying again just now. So the first type of use case is where everything is public. Okay, so typically the output is already public, so I've omitted the label here. But what if we just make the input data public and also the model weights public? You might ask then, you know, what's the point? Well, the point is succinctness, right? So we are gaining compression. Again, there is no way that we can have a whole machine learning model inside a Solidity contract. So we can essentially, well, do whatever machine learning off-chain, right? So we can perform our inference off-chain and then proof on-chain. So to give a more concrete, so essentially it's like a rollup, but for machine learning specifically, right? So to give a little bit of like idea or use case or an example of how this type of use case might look like, I want to present to you, which is a recent ERC standard that I have written. If anyone is interested, you can look up like ERC 7007. I don't think it has been merged on the website yet, so you might have to go into GitHub to take a look. But the idea is you can do something that is like, well, we already know that AI is widely used in the NFT space, right? There is a lot of NFT that is generated by AI or at least generated by algorithm. But the problem is I can say that I have created an image, right? I've drawn an image, but I can say that is an AI generated one, and vice versa, right? So there's a lot of problem with like intellectual property, or how can I even prove that I own this image, right? So with AIGC, AI generated content, the way that you prove you own this image is to show that, you know, you have run through this model and get this output, right? So the idea is, well, we can have a verifiable AI generated NFT by utilizing ZKML. So the kind of the process goes as follow. So you have something like a user proposing a prompt. The prompt would goes into the prover, right? Which the model will split out of course, the output, which is the AI generated media, and then the proof, right? So you need to submit everything to this kind of claimable NFT smart contract. And then this smart contract is gonna verify your proof. And only when the proof is verified, it's gonna allow you to mint it, right? So the idea of this whole construct is that not only are you proving that you own this media image, you're also proving that I'm actually created it, right? By creating it, I am the person who proposed this prompt, or who is the first to propose this prompt into this model. And this is the image I got. So this is kind of like a way to gain like verifiable computation off chain, right? So I've seen a question in the chat. The chat says, what is the progress on ERC 7007? And the progress is actually, we're still discussing on Ethereum Magicians. Thank you, MK, for sending out the link. The draft should be merged into the EIP very soon, but we're still at the stage of drafting. And based on the discussion, there should be a lot of changes coming in the next kind of like edit. So yeah, but feel free to go on to like Ethereum Magician and put down your thoughts. And I'm really looking forward to kind of have like the first AIGC model deployed as this standard here. Right.
Well,
so is there any question?
Yes, I do actually, a follow-up question to the EIP 7007. So from a friend actually, so he was asking, he was wondering if, because generative models are very expensive to prove, and will that in any way affect your proposal, such as it's very expensive to prove, and also I don't know how expensive it is to verify, and will that be possible at the current state of Ethereum?
Yeah, so normally it's much more expensive to, well, we'll get into the trade-off, but essentially, well, prover time and verifier time is kind of a trade-off, right? So usually if it's more expensive to prove, it's a little bit cheaper to verify on chain. And that's usually what we're opting for right now, because we want it to be cheap on chain, and we don't mind doing more work off chain. We also get into like actual numbers, but I guess like for now, the idea is that you can only do very simple models. So don't think of like doing an actual full stable diffusion, because this is probably going to be very expensive for whoever is, volunteering or even getting paid to be a prover, right? So yeah, so the machine that we're talking about, if we want to do an actual stable diffusion, is actually huge, like in the terabytes of RAM. So that's not very feasible, but it's totally possible to do a small scale AI generated model, right? So when we say AI generated model, it doesn't have to be everything that is like as perfect as stable diffusion or DAL-E. It could be something that is trained to do a much smaller image, or really a subset of whatever it's capable to generate. So I think the idea is that a lot of people might be using it to generate like abstract art, pixel art, things that is much cheaper to prove.
Nice, thank you.
Yeah, and also to answer your question, I don't think the cost of the model proving itself should hinder the process of 7007, because it's not really dependent on what model you use. It's just a process or just a recommendation on how this process should look like. Cool. And so that is the first type of use case, which if we were to sum it up in one word or two words, is verifiable computation. But then we can also get into more privacy related use case. So type 2 of use cases is this, which is we have now the input data is still public, but our model weights is private, right? In other words, did I mess up? No. Yeah, no, that's, yeah. Okay, my bad. Let's talk about this type first then. So the second type of use cases is the private input data and public model weights. Okay, again, this is now a more intuitive use case, whereas you have private data, which is something that may be related to personal sensitive data that you want to hide. And you have some public kind of like known model, verified model that is possible for people to trust, right? And this second type of use cases would be kind of anything that is related to privacy or requires privacy, right? So this is kind of one of the space that is the least explored right now, mainly because if you want to have a very good model, typically these models are big, they're more expensive to prove. But this is also one of the, I guess, the most anticipated type of use cases, right? So imagine if we have a model that is publicly known to be very good at recognizing fingerprints or your face, what you can do is we can essentially enable biometric authentication for smart contract wallet. Right, so we don't have to have our biometric authentication happen on our device. Instead, we can have it on the smart contract itself. So that's one. That's kind of the most kind of trustless way in order to perform biometric authentication. The other thing we could probably do is to finally have some kind of private data marketplace, right? So what we can do is, well, for example, I want to sell you an image of something that I've took of the Hong Kong famous Victoria Harbour, for example, right? I want to sell you this image. I don't want to post it online so that everyone can just right click and copy. How can I do that, right? How could I possibly be able to prove to you that I have certain image? Right, so I could maybe have a machine learning model that is very good at recognizing scenery or annotating images. I could have a machine learning model that is good at, distorting and downsizing an image, so that we can essentially have a provable way to tell you that I have this image even before the transaction happened, right? And then afterwards, of course, you can use smart contract to control like how you can actually do the transaction and encrypt the image and send it over. So there, with ZKML, it could make a lot of these like private marketplace possible. Right. So I think this second type of use case is quite easy to understand. So now let's go into the third type of use cases. So again, don't mind the numbering. So the third type of use cases is actually the opposite, right? So just now we have private input data and public model weights. Sorry, I'm hearing some noises. Is it from me or?
Oh, okay. I muted.
Okay. Yeah. No, I was just worried that it's from me. Okay.
No, you're perfect.
Cool. So the public input data and private model weights. Sorry. So again, this might be a little bit puzzling and not as intuitive with the previous type of use case that we mentioned. And so, well, what are we doing with this type of use case? So with this kind of use case, it could be something like a Web2 company or really any company that has a proprietary model that they have, but they don't want to tell you what it is. right? But they also want you to trust them. So they want you to trust them in terms of, for example, they want to prove to you that it's the same model that they apply on everyone, right? So a good example is, for example, Twitter, right? Recently, they open sourced their algorithm, but let's be honest, who is ever gonna actually go and look at their source code or actually run their full algorithm, right? And also, how do you know that this algorithm is actually what is being applied on you when you're using Twitter, right? So there's no provable way, and open sourcing it actually doesn't really help with proving that this is the algorithm they use on you. However, there's actually a better way with, ZK, which is I have this algorithm. I am going to show you that this is the hash of my model, right? So I'm hiding my model weights, but I'm committing to certain model that I'm using with a hash. And what I can do is I can show you that this same hash is the same model that I applied to you, and then to Cathie, to Chi-Tuan, to Kim, to Lucy, to everyone. And the way you show it is just to check the hash that is present in this ZK proof. And that is actually a better way of showing fairness, a better way to, protect proprietary model. And one example that you can imagine what we can do with this type of use case is actually Kaggle or ZKaggle. So for those of you who doesn't know what is Kaggle, Kaggle is a Web2 kind of platform for companies to post their problems, their machine learning problems onto their platform and post bounties. And then for machine learning engineers to try to tackle the problem and submit the model. Okay, so that is what the Web2 version of Kaggle is. The problem with it is that in order to kind of get the award or even get evaluated, you have to share your full source code before you even win the prize, right? So let's say there's 1,000 people or 10,000 people who join this competition. All those 10,000 people will have to submit their source code to this company. Of course, the regulation probably says that, okay, if you don't win, they won't use your model, blah, blah, blah. But this is not a very trustless way of doing it, right? So a better way of doing it would actually be something like a ZK Kaggle or ZKaggle in short. So the idea is, well, you can have like bounty, whereas the bounty is split into like private data and public data. People can use the public data to train the model. Then the model from Python can be translated into like a ZK circuit using some transpiler that I will mention later. And then we can submit kind of this model onto the platform, maybe encrypted. And then we're able to prove that our model has certain level of accuracy, right? So we're not able to score our model that we submitted without disclosing the model fully. And this enables people to kind of have a very trustless way of first fairly evaluating all the models, having a provable accuracy or provable performance metrics without disclosing the source code of the model itself. So this is actually a POC that I've done. Again, with the current limitation, we're not able to do very large models. So this is not like in any way practical use yet, but we're able to kind of at least prove that this concept works with kind of like, so the idea is, so the whole process would kind of look like this. So a bounty provider would submit a transaction and post a bounty. People would submit their model with the approvable accuracy. Right, and then the model the bounty provider is gonna release the bounty, and at the end, when the person come and claim the prize, they are able to decrypt the model for the bounty provider, right? So it's kind of an S-crowd process still, but with a little bit of more verifiability coming from ZK. Yeah, and it's a very short kind of introduction of a more complicated project. So if there is any question, I'm happy to answer as well.
All right, I don't think we have any questions for this one.
Yeah, so if there's no question, then let's move on to kind of talking about where we are now. So as you can see, people are very, hyped about zero knowledge machine learning. That I also realized like people are always very eager to know, but like currently we really don't have any products, right? So where we are at right now for ZKML is really just these 4 things, right? So we have a lot of hackathons actually in the few kind of upcoming Paris hacker houses. Most of them are CK or ZKML themed. So we can expect that there's a lot of hackathons that are going on with a lot of hackers trying to tackle ZKML. We are also at a lot of proof of concept stage, right? So just now the ZK is a proof of concept. We can't really do any model bigger than something that is like something that can work on a MNIST model. So for those of you who doesn't know what an MNIST model is actually around like tens of thousands of little images, which is like 28 by 28. So very teeny tiny images of black and white handwritten digits. So 0 to 9, right? So other than that, we probably need some bigger servers, a lot more powerful machines in order to operate, right? So a lot of the things has kind of like halted in the proof of concept stage. Of course, we're also doing a lot of research, right? Because we cannot get past this proof of concept stage, then we also need to do a lot of research trying to gain a little bit of that acceleration and how to actually like speed up or be able to do larger models. And we are also stuck at more likely server side ZKML right now, right? So by saying server side means that the ZKML the prover has to be a huge machine that is probably on the cloud. As I mentioned, we need like terabytes of RAM. So the problem is if we are doing it server side, then we are not really able to gain a lot of these use cases that is related to privacy, right? Because the whole point of ZK is to have the proof done on device, right, on client side. So currently we're kind of stuck with server side. And I will explain in a little bit like why is it this case. So understanding like where we are at right now kind of brings us into, why we are at where we're at right now, which is the challenges that we're facing. So there are 3, Lucy has a question with respect to being able to run larger models, custom hardware work. England, yes, so that's absolutely true. A lot of like hardware acceleration is going to help. The problem though, however, with just basing on hardware acceleration is that if we're depending on hardware acceleration, we are still most likely gonna be stuck with server-side ZKML. Because the idea is you wouldn't really expect a user, right, a regular user to have that kind of custom specific machine at their home. And as long as we're kind of stuck with server-side ZKML, the problem is still that we don't gain like privacy application. Right, so that brings us to kind of the current challenges, why we are stuck with POC, why we're stuck with server side. And the first challenge is actually very simple. It's about mathematics. It's about the different types of mathematics that ZK and machine learning use. So machine learning models is all about like gradient, calculus, basically everything that will require a lot of decimal points. And hence, usually the best performing machine learning models, when we train them, use floating point weights, right? So at least 32 bits. And this is what kind of makes machine learning models so powerful, is that we're able to gain like those little gradient change at a time. However, CK circuits, if any one of you have worked with CK before, you will realize that we are typically working with integers, right? Or a better way to put it, fixed point arithmetic. So these two kind of mathematical scheme here, right? Mathematical system here, number system here, is inherently incompatible. Well, luckily, the way machine learning, we do machine learning on our phone or our mobile has already helped, right? So our phone is also not as powerful as our computer. So machine learning engineers have been known to how to move like their models into a 8-bit or a 16-bit models using quantization. The problem with quantization is twofold, right? So first of all, you can have post-training or pre-training quantization, right? So pre-training pretty much means that you are trained with the idea of quantization in mind, so that like when you convert to a quantized model, you're not gonna lose a lot of accuracy. There is also post-training quantization, which just means that you train the model regularly, and we're gonna try our best to quantize it, you know, by looking at the numbers, putting them in like quantized bins and trying to get it to work. And with that, actually, we typically lose a lot more accuracy. So this has been a challenge, especially if we're looking at some applications that requires very high precision. So for example, if we're looking for fingerprint recognition, we can't really afford to lose a lot of accuracy, right? Because like that's not a really good thing if we are going to like use it for mass adoption. So that has been a problem. But then there's also good news with this kind of like quantization thing, which is a lot of the large language models, LLM, or the diffusion models, stable diffusion. Actually, the larger model you get, typically they're more fuzzy about the numbers. And typically you don't get as much as a performance degrade when you quantize. So you probably have seen on Twitter, people are like, oh, I got a 8-bit version of the Facebook LLM, which is called Llama, on my computer, right, on my laptop to run. And that's because like larger models typically and generative models typically are more fuzzy with quantization. But the problem again is if we want something that is like, classification based, things that requires higher accuracy, this is typically the challenge. Second challenge is simply too expensive. So as Chi-Chuan also mentioned just now, actually, we all know that this is a problem. So again, I don't really have basis on these numbers. It's just based on like my personal experience and intuition. I think doing machine learning in the ZK right now is around 1,000 times more expensive than doing it regularly. Okay, so what does this 1,000 times more expensive mean? It means that, let's say, if we can run a model on a machine that usually have gigabytes of RAM, in order to run its ZK counterpart is we now need terabytes of RAM. So this is around 1,000 times more expensive, right? Time-wise is a whole different story. So I'm not going to get into time because like time we can probably have like hardware acceleration that can help with it, but the amount of RAM of memory that it occupies is a huge problem. Of course, there is like a lot of solutions that we're trying to work with, and that calls for like research. As Lucy mentioned, we can wait for hardware acceleration, right? So if we have specific hardware that does ZK more efficiently, probably we can have use those instead of like what we have right now and gain a lot of acceleration. This is probably a way to speed up server-side ZKML. For client-side ZKML, we probably need something like a more efficient way to do recursive ZKP. Okay, this is something that I will get into a little bit later when we go into the future. Jin-Suk mentioned, is it necessary to prove all layers of a neural network model? Why can't we just prove last 3 layers of a deep model? That's true. So it is true that actually a lot of people, or at least initially, we were trying to just prove the last 3 layers of the deep learning model. Again, it depends on the use case. For some of the use case that is okay, but I can also easily give a use case that is not, right? So for example, if I want to prove an image, I probably want to hash that image, but at the same time, have that end-to-end process of putting an image into the model and have some result. Just putting the last 3 layers of the deep in ZK would cause the problem of basically either you can tamper with the data, right, and get up to like whatever you want before the last few layers, or you are also risk like exposing some of the details of your data if you choose to like make that process transparent, right? So there's trade-off that you have to do if you're not doing end-to-end. But there actually initially a lot of the practical application is to do that, to just prove the last few layers. So again, it depends on the use case of what you're really trying to do for that specific machine learning use case. I hope that answers your questions. And challenge 3, this is not typical that I put on here, but I recently just realized that there is a huge need for call for action, mainly because a lot of people is interested in ZKML, but actually not a lot of people are actively working on ZKML. So if I were to count, there is literally around 4 to 5 projects that is actively working on ZKML, or at least ZKML is their main kind of business objective. And if you think about it, the analogy that I always make is that think about how many people work in TensorFlow, how many people work on PyTorch, and compare that to the number of people working in ZKML. For a lot of the things, at least for a lot of machine learning operation, we do need a little bit of like customization to make it into a CK template, right? So if there is something that comes out new in the machine learning space tomorrow, most likely we'll need as many people to convert them into a CK version. Right, so I saw a question from Lucy. Other than Daniel, Ken, and I who are working on, I'll give you a few examples in the upcoming slides. I will mention the names as well. Yeah, so we need a lot of people to convert this machine learning operation into CK templates. And there's always a lot of ideas. You always see articles. People are like, oh, you can use ZKML to do this. You can use ZKML to do that. But we really don't have enough hands on deck. So we really need more people to join. And that brings us to, well, what are the libraries or actually teams that you must know in this field, right? At least for the presence. So a few libraries or teams that is working on ZKML that you must know. The first one is actually, I just tried out their Python package today. It's amazing. So this is a library that is actually originally written in Rust called ZKL. Is a library and CLI that converts your models into a circuit directly, into a Halo 2 circuit. And it does, it works on almost like any ONNX file, right? So ONNX is like the file format for a graph. So not just neural network, basically any computational graph. Right, so the way you use it is you have a computational graph that you have in Python, you export it into an .onNX model, a file, and then you also have some signals that you put in a JSON file, and then you just point EZKL to these files to generate a CK-SNARK circuit. Most recently, they have also released their Python bindings. So not only do you not need to install Rust on your machine anymore, you can also just directly do everything in Python. So they have I think a demo collab notebook that you can work on to see the whole process. They have, their team is great at making it very user-friendly and very easy for machine learning engineers to convert it into a CK, to convert the model into a CK version. Yeah, so I love their Python bindings. I was actually trying it out like right before this talk, and it works perfectly well. So this is, so the company doing it is CConduit. So they are, one of the groups that is working on ZKML research. The other library that you must know, as Lucy has mentioned, is Daniel Kang's library. The name is very simple, ZKML, and it's just a framework for constructing proofs for machine learning model execution. It's really kind of a accompanying repository to their papers. So it's best that you kind of read their papers alongside with the code base. Their library actually does much more, but I just want to highlight kind of two things that happens on their library. Mainly, first of all, they actually tackle model training, which is a very interesting thing. The way they tackle model training proof is actually have a backward graph, right? So when we talk about neural network, you have forward propagation, which is inference, and typically training is done with backward propagation, right? So back propagation. So the way you can prove training, at least for simple models, is to have a backward graph, right? So if you are able, if your graph is somehow able to be reversed, of course, that doesn't mean any neural network can be, right? For example, a GAN, right? A generative adversarial network cannot be simply break down into a reverse graph. So, but if you have models that can break down into a reverse graph, you can actually use their library to prove model training as well. Their library also tackle very large model. So they were able to put like GPT-2 or BERT or even some form of diffusion models onto ZK as well. Again, when we say they are able to put it in ZK, we are talking about terabytes of RAM. So that's more like server-side ZKML. But it's very cool that they were able to at least like have these very large models in ZK and have it worked out. And just a little bit of self-advertisement, my libraries. So these are two open source libraries that I'm constantly looking for contributors. I primarily work on CIRCOM for some reason that I will explain later. So CIRCOM, people have moved away from CIRCOM into like Halo 2 for more efficiency and also for the ability to perform lookups. But there's a reason why we still are interested in CIRCOM that I will explain later. But these two libraries are, first of all, a CIRCOM circuits library that performs machine learning. And then also a tool in Python that transpile a TensorFlow Keras model into a CIRCOM circuit. Right. So the problem, I guess, with CIRCOM, one of the major problems with CIRCOM is that I would have to basically construct every single machine learning operations in CIRCOM as a template in order to cover more of like the whole machine learning field of machine learning. So right now, actually, my library only covers certain very common layers that you will see in a neural network, but not all the layers that people are going to use. And the problem with that is that then if people wants to use it for layers that are not existing in the library, they will have to expand the library, which is something that I really hope that there will be contributors to work on and try to expand this library together. Right, and as I mentioned, the reason why we still use CIRCOM at PSE, there are some reasons connected to kind of the research that we're doing. So I want to kind of hop into what we do at PSE for ZKML research. For a more kind of detailed document, you can visit this website here. I will link to the slides at the end so that you will have this for reference as well. So there are three things that we are focusing at PSE team here. So the first thing is actually benchmarking. So we really want to understand like how quantization affects model accuracy. Typically, when we say ZK benchmarking, a lot of other protocols focus only on prover time, verifier time, memory requirement, which is all very important to ZK protocols. But specific to ZKML, we really want to understand how quantization affects model accuracy, or how we can actually avoid a performance degrade from that. So this is something that we would really want to kind of like have a benchmark. And we also have like some grantees working on it already. The kind of second area of research that we're doing is we're also looking into ZK-friendly ML. So this is hugely inspired by the field of fully homomorphic encrypted ML, which they are already very into like studying what are the machine learning architectures that is friendly for fixed point arithmetic. And that means not the neural networks that we know. And there are a lot of other models out there that are not neural network that could have comparable accuracy to neural network. So something like a weightless neural network, which you can refer to this project that we're supporting, could be an option, right? So just use a bunch of lookup tables and a bunch of Bloom filters in order to achieve the same accuracy that you get from neural networks. You can also have purely Boolean circuits. You can expect the circuits to be huge in order to achieve the same level of accuracy. But then again, the beauty of it is that it's purely integer, right? Actually purely just 0 and 1s. You can also have like binarized neural network, which is kind of the same idea, and also truth table net. So all of these like integer-based machine learning architecture would be much more CK friendly. And it's probably worthwhile to kind of explore all of them. One obvious question, of course, is like, if they don't perform as well as neural network, then what's the point, right? But actually, for example, for the first one, the weightless neural network, at its time in the 80s, it's used for fingerprint recognition. So it's actually something that people use in industry and production, and has like enough or sufficient accuracy to be used in production. So all of these like CK-friendly architecture could be something that's very worthwhile to kind of check out as well. And also folding. So what is folding? Folding is actually related to what I say about recursive CKP. So the idea of folding is that you can take a bunch of proofs that looks kind of have similar proof structure, right? So for example, if we do machine learning inference, we might be applying the same model to a lot of data, right? So to different data. So let's say I have 1,000 images. I want to apply the same model to all those 1,000 images. So the folding technique actually allows you to fold all those proofs into one, right, recursively, so that you only have a small overhead in addition to the original proof size. So right now, there are two folding schemes. Nova works on like the R1CS constraint system, which is the constraint system that Circum use. So that's why we're still working with Circum instead of Halo 2. But there is also Sangria, which work on like Plonkish scheme. So with Sangria being implemented in the future, you can possibly also use folding on, you know, all the existing libraries, like for example, ECKL or Daniel's ZKML library. We can possibly also fold them and gain some performance acceleration as well. So yeah, so we're also looking to fold, you know, all sort of different things. So one thing that I mentioned just now is just folding inferences. But when you think about machine learning, there's actually a lot of repetitive operations, right? Like if we do convolution, it's really doing the same operation over and over again, convoluting on the same image. So possibly we can fold that as well, right? So if we are able to do recursive acceleration in pretty much every single area in ZKML, then it's possible that we can gain a lot of acceleration from this kind of recursive folding scheme as well. Right, so these are the kind of the research directions to look into if you want to get into like ZKML research and the most cutting edge stuff. Right, so where to start, right? Which is, I think a lot of people coming into this talk will probably want to know, okay, I've heard so much good things or interesting things, exciting things about ZKML, where to start for this? Well, if you have some machine learning background or know some machine learning engineers that would be interested in ZK, interested in crypto, I would suggest first, of course, play around with ECKL, convert some existing models into its ZK counterpart, right? Try to deploy some model on chain and play around with it. And also start building or really thinking about applications. So some applications could involve like algo trading or even doing biometric authentication on fingerprint. So I will have a more concrete example of algo trading in a bit, so I won't go into it yet. But yeah, but you can think of like what kind of applications that you can build with models that might not be affected by the CK quantization so much. If you have a ZK background or want to get into it, you can first start off with studying, CIRCOM, Halo 2, Nova, and then help like machine learning engineers actually turn their models into a CK version, or contribute to open source libraries, or like join our research initiatives. And I'm really looking forward to whoever wants to deploy kind of the first AI GC NFT collection. I'm very happy to help. I actually already have some people telling me that they're interested, but they don't know like how to get into it. Their company might have a use case for that. And I think it will be a very interesting and, finally a feasible practical project that people can see about ZKML, so that it's no longer just like an idea, but something that people are tangible and able to see the application of. And speaking of application, just kind of two applications that would keep everyone excited and inspired. And they are both by Modulus Labs, which is the fourth, project that is working on ZKML. And so just now I mentioned algo trading. Actually, there's a bot that is already deployed by Modulus Labs that is doing trading with AI, right? So in the essence that they have a model that works on investment, right? And they are able to prove that this decision of the investment or this action that this bot perform on chain comes from this AI model, right? So you can think of this as a lot of use case. Of course, this is more like a game where people are, are just contributing and see what and donating to see how this bot will work out. But you can also imagine, a lot of investment DAO, right? Instead of trusting some people to do the correct action, you might as well have some kind of an algo trading bot that is provable, right? So this provable bot would be able to submit a proof alongside with their investment actions, so that you can have a verifiable and trustless way to perform all the investment actions, from a DAO perspective. So this could be like something that is very fun to do. And also you can gamify the whole process, right? So this is actually another project by Modulus Lab, another fun one. Again, it's online, so you can play around with it as well. So you can pretty much like bid for a chance to play against an AI on chess, right? So there's a AI that is known to that knows how to play chess, and the idea is that when it's going to submit its proof along with the proof that this actually comes from an AI model, right? So what it proves is that you're not playing with someone just behind the machine, right? You're not playing against another human that is like pretending to be AI, right? So this is again a very kind of fun idea of how to make ZKML practical. So with that, I would say let's brainstorm what is the possible ideas, and I look forward to kind of like the discussion after this talk as well. Right, so that's the end of my presentation today. This is the QR code to my link tree, along with like the first item is actually today's slides, so you can click onto it. But I will probably go back and fix a little things. I did realize there was some error in there, but then the link should be like real-time updated as I am fixing it.
Cool. Well, Cathie, you're worried that 1 hour is like something that's too long, but I think 1 hour it's just nice because you covered through everything, and I think everything is detailed. I enjoy your talk. I think everyone does as well. So thank you so much again for volunteering to speak to the community, and we are always very welcoming of you and of course the PSC team. So let's do a much casual chat. Let's fireside chat. We always start off our fireside chat with a bit of introduction and a get to know session. Fun fact, Cathie is actually my ZK teacher. I'm going to say it many times throughout this entire call. And back then she was one of the, I think, one of the lead instructor for this ZKU thing, and I participated and I learned how to run my first circum circuit from Cathie. So there you go. For those who are wondering how I learned from Cathie. And enough about me, but what about you, Cathie? Like, how do you get into the space, the ZK space, the crypto space, and how do you get into the ZKML space?
This is one of those stories that you will feel like you can only hear it from like Web3 or crypto. So basically, I wasn't in the crypto space until end of 2021. So right after the crypto summer, which is good, right? Because like then I'm not in for the hype. But basically, I was tasked with creating the syllabus or the content for Zero Knowledge University. So the program that you joined. The idea is that at that time I was working for Harmony Chain, so an alternative EVM L1, and they wanted to onboard like developers into ZK. And they thought that it would be good to find someone who is more of an educator and learn ZK rather than have someone who is good at ZK and doesn't know how to teach. So then that's why I was hired. I needed to learn the basics of ZK and Circum in, I think, 2 or 3 weeks before I taught you guys. So that was kind of like how I joined the space, kind of, yeah.
Nice. Your 2 or 3 weeks course is much harder than our 1 month, 6 weeks course.
No, I would say like it's very wonderful right now. There are so many resources. Like back then, if you search Circum, I think the only thing that pops up is the official documentation. And it's not even that like complete. So there's a lot of like trial and error, but it was a fun process. You definitely learn a lot more things like from just really trying it out.
Cool. And now you have joined the PSC team. And what are you involved in the PSC? Because we know that PSC has many projects. And I know that you are more involved in the ZKML side. Like, are you specifically researching in any areas of ZKML?
Yeah, so well, actually, all those research directions that I've mentioned in the slides just now is really just me at PSC right now. So right now I'm more tasked with like thinking about the high level directions. Of course, I also do a bunch of coding, trying to put out some proof of concept as well. But yeah, but that's why we always want a lot more people to join, because there were so many ideas that we want to try out, but there's just not enough like people to do so.
Cool. And okay, just to remind everyone that feel free to also leave your question for Cathie. Not every day we get to ask Cathie in person, like this today. So we have one already. Currently, what is the biggest obstacle in your opinion for implementing the tooling for ZKML?
I think, to be honest, like people might think it's the speed, the prover time, but really I think it's, from a business or commercial perspective, it's probably more meaningful if someone has the first use case. Like for example, with ECKL, actually you can already convert maybe 90% of the models that people use nowadays into its ZK counterpart, right? So the tooling is actually there, but no one is using it or no one is interested in developing it further because there's no actual application yet. So I think we really need someone who is like interested in building the first application. So as I say, be it like an AIGC NFT model, or be it like a fun game, like what I showed you with Modulus Lab just now, like someone needs to have the first use case that people are excited about.
Cool. And Alumni asked a very interesting question. So the computation model to run, the computation requirement to run ZKML, because ZK itself is also a very computational exhaustive. So what are the requirements to run ZKML?
Right. So as I've mentioned in the slide just now, my rough estimate is around 1,000 times more expensive. That's not even counting the time. The time is crazy, but time can be improved by a lot of hardware, acceleration. But the biggest problem is probably like memory requirements that we're facing right now. So when I say 1,000 times, it's like a typical model right now, an LLM model, we're talking about gigabytes of RAM, right? I can run it on my GPU that has 32 or 16 gigabytes of RAM, but we will need like terabytes of RAM in order to do the same thing in ZK. So that's much more expensive, actually.
Cool. And actually, some of us here were participating in a previous hackathon. We were building some ZKML stuff. It was, I think they call it Sephora or something. So the idea is to protect users' interacted contract using AI model. And I think the team was facing a problem whereby the model that was trained by the Onyx file couldn't be nicely converted by EasyKL. So that was the problem that I think the 10% edge case that you were mentioning. So with regards to the question, tooling is very important and EasyKL is not perfect. And what are the and floating point numbers is not supported, or at least they have to be quantized, and you give up accuracy. So are all these things a factor in people adopting ZKML? Like, or do you think this will get improved over time, or do you have a strategy in mind on how this gets improved over time?
Oh, that's a very good question. Yeah, I think, to be very honest, like with a high performance model like that they're trying to achieve, most likely what's gonna be required is to really treat it like a AI project more than I guess blockchain project, in the way that, like, to perfect a model in machine learning space, like if anyone come from the machine learning space or AI space, they will realize is that like there's a lot of fine tuning that you have to do. There's a lot of optimization that you have to do. And I feel like for those critical models that you want to perform, it's probably not good enough to use EasyKL, right? It's probably more casual use case. For example, if I'm doing like an AI generated NFT, sure, right? If we gain a little bit of, lose a little bit of precision, it's fine. But if with very precise model, I think there's a lot of like manual work that needs to be done. And frankly, we don't have enough machine learning experts in the field that is interested in doing that. And that is also one thing that I'm trying to like think about, like how do we attract machine learning engineers into the space?
Actually, it's good that you asked this question, because I think in the previous hackathon, if so, I've seen a few ZKML machine learning based projects popping up. So I do expect to see them even more in Paris. Hopefully that will excite you. And Maxwell asks, so are there proof system designs specifically for linear algebra operations as opposed to algebraic circuits or R1CS that are more efficient in proving MLs? I was about to ask a similar question, but I will let Maxwell ask first.
That's a very good question. Actually, no, not that I know of. Not for linear algebra operations. I know in, like, for example, in Halo 2, a lot of people are hacking the way, not for the not for the linear algebra operations, but for the non-linear operations like sigmoid or hyperbolic tangent. They are hacking the way by making everything a lookup table. But that also have a trade-off, which is like lookup tables could also be very expensive, and it's not the best way if you build everything as a lookup table, right? Essentially, you can have a model that is just a huge lookup table, which is actually what the weightless neural network is. But yeah, no, not for linear algebra. I think for linear algebra, people are looking more on hardware acceleration.
Cool. And a follow-up question by Maxwell as well. So when you said that you need like around 1,000x larger RAM, are you referring to some highly optimized versions like folded PCDs, IVCs, or other naive implementations?
I haven't really looked into Daniel's code base, but I would say I wouldn't say it's a naive implementation, but definitely not a highly optimized one. Like I don't think they use IVC or folding in the kind of the version that they made for GPT-2. And that's the 1,000 times I'm referring to. But yeah, not a highly optimized version for sure.
So another question by me. So Starknet has been pushing Cairo, and they claim Cairo to be a very easy to use language as compared to writing raw circuits in RNCS or in Plonkish arithmetic. So have you explored Cairo? Like, do you think Cairo is a suitable language to write ZKML? As they claim that it's a easier way to write ZKMLs and probably a more efficient one. What do you think?
I have not explored Cairo 1, I must be honest. Like the new Cairo, I have not explored. So I cannot say much for it, but I do realize that they said there is an easy conversion from Circom into like a Cairo script or something like that. Like that's what I heard from someone. So I think it could potentially be very, very interesting. Yeah, but I mean, I know too little about Cairo to say anything. But at the same time, I don't know if like it's if I write it in Cairo, does it mean that it also goes on chain, like as a part of the smart contract, or how does that work? Actually, question back to you.
So so I would take this opportunity to talk about Cairo a bit. So Cairo, it's a general programming language, and you use Cairo as a subset of all Cairo's functionality deploy contract. So what you can do with Cairo is that you can write a general program. So the Cairo prover is written. So the sharp prover by Starknet is actually written in Cairo. The ZK EVM Kakarot that is recently being invested by Vitalik and stuff like that, also written in Cairo. So Cairo is a language that allows you to generate proofs. Yeah, so that's the strength of Cairo. So
that sounds perfect. Yeah. Actually, yeah, no, I'm really looking into kind of exploring that for sure. Yeah.
Yeah, I was about to say that I'm definitely thinking of like writing using Cairo to explore some of the ZKML world. So yeah, again, we'll see how it happens. Or the community can take part. So Wenkang asks, there are projects out there that does general purpose verified computing like RISC-0, which allows application running on top to be provable. What would be the differences between making ML models runnable on ZK VMs and using the current ZKML libraries like EasyKL? So
that's a very good question. I think I wouldn't say for sure, but I believe right now, at least having specific purpose circuit is still way more efficient than running on ZK VMs. However, there is a good thing about running on ZK VM is that I know RISC-0 is looking into something called a functional commitment. So one thing that I didn't mention in my talk just now is that like I mentioned that model weights can be private, but actually we're not hiding the model. So the model architecture is actually public. And for a lot of use cases, that actually defeats the purpose of model weights being private already, because you can actually retrain the model. Like once you know what model people are using and what data people are using, you can retrain it yourself. For the late models like OpenAI is one, even if you know the architecture is not enough. But yeah, so with RISC-0 and with like their implementation of ZKVM, essentially what you can gain is something called a functional commitment, which is you get a hash of the circuit that you're running. So you can hide what the program you're running as well. You can just like provide a hash and say that, hey, this is the program, the hash of the program that I'm running. And you can trust that I'm running the same program over and over again. So that's a good thing about RISC-0 and ZKVM. But I think like probably specific purpose circuit is still more efficient.
Cool, but it would be much harder to write those circuit, I imagine. Way much harder than using a ZKVM.
That's true, but even with ZKVM, you still need to have an understanding of ZK, like what kind of signals you need to hide. And you're still kind of restricted to fixed point arithmetic for the most part for now. So
interestingly, I do have another question regarding fixed point arithmetic, which is something that the team faced during the hackathon process. They realized that EasyKL doesn't support fixed point arithmetic. Any tricks or any hack that allows can easily bypass the fixed point arithmetic limitations of ZK?
Yeah, that is an interesting problem they encounter, because I believe EasyKL does have a heuristic to help you convert that. I don't know, maybe that heuristic is not good enough for the range of numbers that they have in the model, perhaps, but in a way that like ECKL should handle the quantization for you, which is like basically you have a bunch of floating point numbers, right? Just break it into, I don't know, a bunch of steps and having like a quantization, a scaling for it, basically, right? So there is quite a lot of ways of doing it. In my libraries, I tend to do it a very naive way, just to make it like more compatible with a lot of things, which is, you know, for example, if you have a number of 0, 1, 2, 3, 4, 5, 6, blah, 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 just turn it into 123.45. Sorry, 1, 2, 3. Or if you want more precision, turn it into 1, 2, 3, 4, right? Just scale it up by the power of 10. Yeah, but of course, then the problem is you run into overflow with fixed point arithmetic if you're scaling up all the numbers.
It's a hard problem to solve.
Yes.
So Wen Kang is eager to know that if there are any plans of making PyTorch 2 Circom library or something.
There is actually a project that does that. I will put it, I think it's ZKML Ushikoma. I'm not sure if they're still maintaining it. I think they are. Well, actually, it looks like they're not active, but they are pushing a release soon. Which is a Circom transpiler for network for ONNX, so PyTorch. Yeah, I think not only are they making a big release, they are also making a model training version of it. So yeah, there should be updates coming up. I'm not sure when, though, probably in the next few months or so.
Yep. Right, cool. And one thing that for myself, so you mentioned a lot that the PSC does a lot of research work, at least on the ML side, using R1CS. And interestingly, Hello 2, PSC has a Hello 2 version. Hello 2 has a PSC version. And I assume down the line there could be some conversions from, I don't know, R1CS to Plonkish arithmetic. So how much of a rework do you think that it needs to be done, or everything can be nicely translated to a Plonkish arithmetic circuit?
That's a good question. I mean, right now, like for the few projects that I've mentioned, pretty much anything except what we're doing right now is in Halo 2. So those are already kind of like natively in Halo 2. But if you're talking about Circom to Halo 2, I don't want to speculate, but I think it will be a very lengthy process. Most likely what will happen is that there will be lookup capability added to Circom instead. So the other way around, which is a thing that a lot of people are talking about, right? Like Circom is okay if we are able to add lookup at some point, which is kind of changing the scheme really. So, but yeah, so I'm not sure how that's gonna work, but people have been talking about it for sure.
But interestingly, Circom supports Plonk as well, right? Like, and Plonk,
Yeah.
one of the key strength of Plonk is lookup tables. So I don't know, I haven't been using Circom for a while. So at least the newest version, like don't they support lookups for Plonk? That'll be interesting to see that they are not supporting lookups for Plonk.
Yeah, I think it's a trick on how to do it at a DSL level, or do you go in and add after the conversion from R1CS to Plonk, right? Because I think it still goes from like, no, actually it goes from directly to constraint. Yeah, I don't know how that's gonna work. I think it's still like how to really integrate it at a DSL level would be difficult.
I don't know. We have to ask Jordi one day.
Yeah. I think there's
yes.
Question with
Lucy has a question. I saw 852 chat with Scroll Vincent recently. Any direct talks with L2s to implement ZKML, or current challenges of causing L2 ZKML implementation away? Well, so basically, yeah.
I think, to be honest, the the same thing that I mentioned just now should apply to anything that is EVM equivalent, I would say, EVM compatible. So if we want to, and this, I think this is still relevant even for L2, like, because it's not just a gas problem, right? It's a size problem, it's a computation compatibility problem. Like Solidity isn't really designed for machine learning. So I think it, like what I said just now, pretty much is like as relevant to L1 or, you know, any blockchains really. But yeah, no, I don't think there's any like particular plans for L2 to or L1 to like implement ZKML, at least not that I know of. But
Yeah, speaking of L1s, when I realized that EZKL is using Hello 2 as their proving scheme, and we know that the verification time for Hello 2, it's I think log n or something, and it needs support. I don't know if no, I don't think EZKL supports the recursion of Hello 2. So I reckon that if the proof size the proof gets very, very big, it might even exceed the gas limit of Ethereum. Is that true? I mean, that's just my speculation.
yeah, I think the first thing we encounter is probably it exceeds the contract size limit first, before we even talk about gas limit. Yeah, I have not seen cases that we exceed the gas limit just yet. I think like even with Halo 2, actually recently one of our PSE grantee is working on, you know, converting the weightless neural network into Halo 2, which was originally worked in another DSL. And he was able to do some optimization actually to tackle that problem as well. So even within how you construct the lookup table itself, there is a lot of like optimization that you can do to really make it fit the size. But so far, I think if you are able to fit into the contract size, the gas limit is fine so far.
Okay. Right. Cool. I ran out of questions, and any last call by the? Oh yeah, actually I got one more. So a very fun question. So because ZKM in the EF basically you are like only one working in ZKML. Are you hiring? Are you looking for assistant? Maybe this is a good call for assistance.
Yeah, no, so we are, I don't think we are hiring for research roles specifically, but we are constantly looking for projects to support. So a lot of people who are doing ZKML research actually work with us as grantees. Before I worked full-time at PSE, I was actually a grantee as well. So the ZKAGO project that you saw, it was actually my grant with PSE. So if you are interested in working on any research direction that I mentioned just now, or if you have another cool idea about ZKML, you know, just tell me all about it. We can discuss and see whether it fits like PSE direction, and when you can make it a grant that can support you for at least a few months to work on this like full time.
Nice. So for everyone out there or listening on YouTube, that wants to explore ZKML, so hit Cathie up, and you may get a grant for your effort. Cool. Round of ideas. Lucy's thanking you for coming, for being for your time and for the talk. And I think that's all for our questions. And I want to end this call by saying very thank you to Cathie. Nice 1.5 hours of Q&A and a very informative session. Hope to see you again in Paris, and and we always welcome you to visit Malaysia as a speaker, or even if you come for the Nouns run, you're more than welcome. So
and ETHKL in October, right?
Yes, ETHKL in October. Yes.
Cool.
I actually contacted Adrian, side topic. We actually contracted Adrian for like a sponsorship, but they lack bandwidth for PSE to support. But you can come as a speaker.
Sure. Yeah.
Let me know.
Cool.
And that's all. I'm gonna stop recording. But that officially ends the